let's talk about volts, amps, and resistance, what they are, how they relate to each other, how you can use them. First, I'm going to do a demonstration and try not to kill myself. Let me tell you something. I've been shocked off of these before, and it is not pleasant. Anyway, we'll do a demonstration. Then I'm going to make an analogy to volts, amps, and resistance, and I think that analogy will really help you wrap your head around what they are and how they relate to each other. See, one of the problems with electricity is you can't really see it, except in this case, and also you can't really get your hands on it, and if you do, you'll regret it. But you know what I mean. You can't physically work with it. It's not like a material that you can handle. So I think my analogy will really help with that. Now, on to the demonstration. What is this? This is a oil igniter, oil furnace igniter. And if you haven't done a lot of work with oil furnaces, you may have never seen one of these, but these little suckers put out a lot of voltage. What they do is, this will be upright like that, and they send voltage out to two electrodes that will arc in front of the oil nozzle. So when you get that little mist of diesel fuel going out, that little arc is what turns it into the flamethrower that is an oil furnace. Now, if I want to test this, I can draw an arc across these. You see it'll go so far, but only so far. And that will shock the shit out of you, let me tell you. It's a wicked little arc. So what's going on? Well, there's so much voltage there that the electrons are wanting to get from point A to point B so badly that they will actually ionize the air and make the air conductive in order to jump from one point to another. So what's interesting is if I were to put this in a vacuum, I could not draw that arc. What that arc is actually traveling across is air. So I think that's pretty cool. Let me get this out of the way, and then we'll talk about the analogy. Let's go over some math, and then we'll talk about the analogy, and I'll try to make the math quick and painless. So volts, current, and resistance are all related to each other through this formula. This is called Ohm's law. Volts, current, resistance. I remember this easiest by writing it this way, where it just spells out ver. Not that ver is a word, but you know what I'm saying. Now, you can manipulate this formula to get any one of these variables that you want. So if I wanted resistance, I would just take the I and move it underneath. And if I wanted current, then I'm just going to move the R underneath. So those are the three forms of this formula. All right, on to the analogy. So electrons moving through wires, well, that's a little difficult to conceptualize. Let's talk about water moving through a pipe, because we can all relate to that. Now, in this analogy, I'm just going to be drawing things out and talking about things as if it's DC, which is fine. AC does some weird stuff, and I did a video on it recently, but the truth is, with this formula and just thinking about it in general, it's okay. We'll just, these principles still apply even though AC does some weird stuff. So in my water circuit, I have a pump. I have some pipes. I've got a water wheel. And then I've got a return. So without a return, I can't really do much, can I? And that's why with electrical circuits, you need a complete circuit. I got a power source, pump, battery. I've got pipes. Those are like wires. I've got a resistance, a water wheel. It's kind of like a light bulb, right? And I got a full circuit. So that's the analogy. Now, in this circuit, what am I concerned with? Well, one of the things I'm concerned with is PSI. How much pressure is in this circuit? Another thing I'm concerned with is flow. So I could have a lot of pressure, but let's say my pipes are corroded and I just get a little teeny tiny area where I can move water through. Well, that's not much flow. So it's not just PSI. I want to know flow. How many gallons a minute are we moving? And then, of course, I want to know resistance. Is this water wheel super hard to turn or easy to turn? Oh, my spelling is so horrible. If I spell things wrong, ignore it. Sorry. If I mix up some words, yeah, you know what I'm saying. So anyways, just ignore it if you need to. All right, so my pump is pumping water around here. Now, how are these related? Let's just first talk about the utility supply. So the voltage supply that your utility company feeds into a building, your house, whatever. Why is that so dangerous? So if you've ever seen, if you have not seen a video of arc flash, I would highly recommend you look it up. What they do is they wheel these mannequins up to breaker boxes and create an arc flash and just nukes them. I mean, they're just melting down. It's incredible. It's absolutely incredible. Why? Well, we've got really big wires. Think about that like really big pipes. And then, so we can have a lot of flow. And then we have pretty high voltage, so pretty high PSI. So getting a hit off a utility, like in an arc flash, is a lot like getting hit with a fire hose. You can just put out a lot of power in a very, very short amount of time. And that's what watts is. Watts is just, with watts, we just want to know, okay, how much power, like what is this thing capable of? Well, there's two elements to that. We want to know what's the pressure, what's the volts, and how much can we flow. And watts includes power factor. We're not going to talk about that right now. Just forget that for now. So PSI is pressure. Now, the technical term for volts is electromotive force. And what that's describing is how badly do electrons want to get from point A to point B? Is it really bad? Is it like with a oil furnace transformer where it's 30,000 volts bad? Like they got to get out of there so bad that they're willing to ionize the air and make a jump to get where they want to go. See, that's how high PSI can get places that low PSI can't. With flow, we're just talking about amps in electricity. And an amp is just how many electrons can move through in a point in a given second. And that number is really, really high, stupidly high. Let's see, I looked it up here. It's 6.242 times 10 to the 18th electrons can flow every second in 1 amp of current. So that's a lot. And then resistance, we measure that in ohms. All right, let's talk about, practically speaking, what's going on in this circuit and how does it relate to this. Okay, well, first of all, let's just talk about a fuse. What is a fuse? Well, a fuse is like a little bottleneck in an electrical circuit that says, okay, I'll let this many electrons through, but if too many electrons try to get through, I'm going to start building up heat. Think about a crowd stampeding out of a football stadium. If they're all trying to go through a little door, well, you're going to get a lot of bumping around and anger and, people getting stomped to death. Anyways, electrons like room to move. They don't like to be shoved through a little tiny door. And when they do get shoved through a little tiny door, you get heat and you get boom, a fuse opens. So if we were to crimp this pipe down and make it weaker than the rest of the pipe, so let's say this is all steel and we just put in a little vinyl tube right here. Well, that tube is going to protect the circuit, because if we got too much PSI, boom. Too much flow, also boom. I know the analogy doesn't perfectly work, but you know what I'm saying. So how do these come into play? Well, with my pump, let's say it's variable speed, and I'm moving a certain amount of PSI, or I'm creating a certain amount of PSI, right? And then I double the speed and I double the PSI. My restriction stays the same. Well, look at how this formula works out. If I increase my PSI and this stays the same, this has to increase in order to keep this formula in balance. So if I have 1 volt and 1 ohm, I get 1 amp of current. If I have 2 volts and 1 ohm, I get 2 amps of current. And that makes sense, right? If I'm going to increase my PSI, my flow is going to increase. All right, what if I make this water wheel really hard to turn? What's that going to do to the flow? Well, it's going to decrease it. So if I make this a big number, let's say it's 1 to 1, so I get 1 amp of current. I keep my voltage the same, but I make this 2 ohms. My current is now half, so my flow is half, because I doubled my resistance. So you can see how the amount of a resistance in a circuit matters. And if you have no resistance, then what happens? Your flow gets too high. And that's why if you have no resistance in an electrical circuit, you burn up wires, because now you're allowing so many electrons into the circuit, and they have nothing holding them back. So those electrons are trying to get out and get around, so much so that they will bump into each other and create all this chaos, and then boom, your wire burns up. And that's all a fuse is, really, is just a wire that's not as conductive as the rest of the circuit. So it limits the amount of electrons that can move through it. Okay, let's talk about practically some of the things that you might measure in this circuit if different things happen. So let's say our pump is putting out 24 PSI, and obviously I picked that number to correspond to 24 volts, like the control voltage in HVAC. And I've got a valve here that I shut off, so I just stopped the flow. Well, what am I going to measure over here? 24 volts, right? Because eventually my water is going to move through the restriction and build up pressure over here, and everything's going to equalize. So we have 24 and 24. And this is why on like a contactor that's off, let's say I have 24 volts going to the contactor, but I have a common over here that's switched off. If I'm measuring 24 volts to ground, what am I going to see on this side? 24 volts to ground. And if I measure here, what am I going to see? 0 volts, because I've got 24 on this side and 24 on that side. So a meter doesn't care whether there's voltage somewhere or not. Like I can have 24 volts here but still measure 0. Why? Because all the meter is telling you is the potential difference between one point and another point. If there's no potential difference, then electrons don't want to flow, and your voltage then is 0. So the meter is just saying, okay, you've got me connected here and here. This is how bad electrons want to get from this point to this point. So with an oil furnace transformer, it's pretty bad. It's 30,000 volts bad that they want to get from point A to point B. Now over here, if I have this switch open, these electrons don't want to go anywhere. They have nowhere to go. There's no potential difference. That's why you can measure across this and there's 0 volts because there's no pressure drop, there's no voltage drop, see? Now, if I open this valve and I'm allowing flow now, okay? So this valve is now open and I've got flow. What's going to happen? Well, think about it just like a refrigerant circuit. I got my pump. I go up here, I've got my metering device, all of my pressure is building up here, and then what happens? After the restriction, you got pressure drop. Now in electricity, this just drops down to 0. And that's why if you measure across the contactor when it's on, you're going to see 24 volts. Because the electrons are what the meter is telling you is that if the electrons had a way to jump around this, they would. So if you took a wire and hooked it here and went over here, they would say, nah, we don't want to go through this. This is too much work. Boom, we're just going to jump around it. And they want to jump around this 24 volts badly. You know what I'm saying? That's how bad they want to get around this resistance. So if I switch my contactor on and I measure, now I've got 24 volts at the contactor. I thought it would be cool to take what we learned in the analogy and apply it to a real troubleshooting scenario. So we have a thermostat here. That's supplied with power from a 24 volt transformer. The thermostat goes out and powers a little relay, maybe for the blower or something, whatever. And then the relay obviously has a connection back to the transformer through common. Now let's pretend that this relay is one of those ones where you got insulated spades and they like sink down in the plastic housing. So it's really hard to get a measurement on the relay. But you do know that the relay is off. So you get your meter, you unplug the wires, and you bring them up here to your meter, and you hook in, and you see 24 volts between this wire and that wire. It's a bad relay, right? Well, not so fast. To be extra thorough, you go and just get a contactor, a sequencer, any kind of little 24 volt load out of your van. So I'll just draw in a contactor here. Then you take jumpers and you connect them up to the wire, and the contactor doesn't activate. So you measured 24 volts open circuit, but then you hook up a load and this known good contactor still doesn't activate. So what's the problem? Well, you take your meter leads and you stretch around and you measure 0 volts now. So what is going on? Well, somewhere in this circuit we have a resistance. So imagine this is a garden hose and I pinch it somewhere and then I cap the end off and I take a PSI reading. Well, I'm going to see 60 PSI because I got it pinched, but a little bit of water's getting through and it's building up because I got it capped. If I take that cap off, and then what? We have no pressure, just a tiny little trickle out. Where's our pressure? Well, it's upstream of where I have it pinched. So no pressure, no pressure, no pressure, upstream pressure, right? We have a resistance in this circuit. How are we going to diagnose that? How are we going to predict where it is? Well, we keep our load in place. And let me just say that loaded circuit tests are always the best kind of test to do on an electrical circuit, as long as you can do it safely. I've got a test light that I modified for 24 volts AC that I'll use for this, so I don't have to try to rig up a contactor or anything. But we want to keep our load on there because we want there to be flow. We don't want this to be like a capped garden hose. We want there to be flow. We want the electrons to be able to move freely in the circuit. So we measure here, and by the way, we keep our lead on common, let's just say our black, onto common. And we take our red and we measure here, 0. We go to the thermostat, 0. 0, 24. 0, 24. So now we know that our resistance is somewhere between this point right here and this point right here. So there's some kind of high resistance in this thermostat wire that's going from the transformer to the thermostat. Well, that's how you can use the analogy, and there's other ways to use it as well, but whenever electricity is doing something weird, there's always a reason. Electricity always follows the rules, and that's one thing that I think is just so cool about it, is that you can always predict what it's going to do, and if it's doing something you don't understand, that's just because you don't understand. It's not doing anything that it's not supposed to do. Well, I hope that was helpful, and that will, if you didn't already know this stuff, that will really increase your ability to troubleshoot electrical circuits and to be accurate with your diagnostics.